To this point, we've gone through a history of Greek atomism, which was primarily philosophical in nature, to a more pragmatic program of atomism in John Dalton. And we're going to eventually look at 4 historic models of the atom, and we're calling Dalton's atom our zeroth model because there's really not much to it. You can't ask Dalton the question, what's in the atom, because he's going to assert that is an unaskable question, because by definition his atoms are the smallest particle, and he's borrowing that Greek definition of uncuttable. And you remember the 4 parts to Dalton's atomic theory. All matter is composed of atoms. They're submicroscopic and indivisible. If you have 2 atoms of the same element, they're going to be identical. They combine to form compounds in whole number ratios. You can't have part of an atom. And then finally, chemical reactions occur when atoms rearrange. And this last one is not to be taken lightly, because it's kind of a death blow to the ancestor of chemistry, alchemy, who sought to convert base elements into precious elements like gold or silver. And what Dalton is saying is that's a hopeless endeavor. That all chemical reactions are the moving around of the Legos, they're the rearranging of atoms. It's a massive demystification of chemistry. But other than needing atoms to exist in order for Dalton to get on with the work that he wanted to do, which was primarily weighing and cataloging the mass of different types of atoms, he doesn't have any other strong experimental evidence that atoms even exist. Later in the same century, a guy by the name of Robert Brown is observing the motion of small, we might even say microscopic particles in fluids, so liquids or gases. And small particles suspended in a fluid, rather than moving in straight line trajectories or momentums that we might expect, they move in really erratic, herky-jerky, twisty-turny patterns. And so that it's the motion of those particles. So if you look here on the bottom right, you can actually trace the path, or we're tracing the path that you might get out of a dust particle suspended in a fluid. We can actually measure these by using radioactive tracers on the dust particles, and you can, because a camera is going to pick up that radioactive glow, or a particular type of camera, we can do time-lapse photography and measure these patterns. And what you find is they do move in these really erratic motions. Well, these are constant changes in momentum in the direction of the particle, which can only happen if there's a series of forces exerted every time this thing is changing its motion. And so what Brownian suggested is that these changes in momentum are the result of submicroscopic particles, things on the atomic level, bumping into these dust particles continuously, constantly causing the change in motion. And we refer to this as Brownian motion, or the random movement of particles suspended in a fluid caused by the collisions of either the atoms or molecules that make up that fluid. And so again, this is just some evidence that things, at least on the atomic level, have to in fact exist. And you've seen this if you've ever watched snow fall on a still night. When there's no wind blowing and the snow is falling outside, it doesn't just fall straight down, but it kind of moves around erratically as it falls to the ground. Or you might think about LeBron James and his pregame ritual of throwing the talc powder up in the air. If you watch that talc powder as it kind of descends to the ground, the individual particles, this cloud of talc, kind of moves in these really erratic patterns back and forth as they fall to the ground, and that's air molecules actually bumping into them. So this gives us some piece of evidence that things on the atomic scale exist. Again, roughly around the same time, we moved to a guy by the name of William Crooks, who, other than having the world's most fantastic mustache, take a second and soak that in. It really is kind of fantastic. William Crooks is famous for building and designing what were known as Crooks Tubes, or cathode ray tubes. And a Crooks tube is simply just a glass tube where all of the air has been evacuated out. And then two metal electrodes are hooked up in various places in these tubes, and then an electric current is run through these vacuum tubes. And a really interesting thing happens when you do this is you get this weird beam, or this weird green beam of light. And Crooks didn't quite know what to make of this, but he certainly thought it was pretty cool. And he took it around and showed a bunch of people, hey, look at what I've been able to do. And they played around with different sizes and shapes and different places of, placements of the electrodes to generate all kinds of weird glowy lights. And so this was a phenomenon that many scientists in this time period would have been aware of, and a lot of people did various experiments to try and figure out what was going on here. Well, one place that the Crooks tube was being investigated fairly seriously was at the Cavendish Laboratory in England. Cavendish Laboratory is super famous because a whole whack of really interesting and scientists who were important to the history of chemistry held the head professorship at the Cavendish Laboratory. James Clerk Maxwell is famous for a bunch of work he did on electromagnetic radiation, but we want to focus in on these two guys, J.J. Thompson and Ernest Rutherford. Rutherford actually worked for Thompson at Cavendish, went away and did some other research in Australia, and then came back to take the professorship after Thompson retired. So Joseph J. Thompson, or J.J. Thompson, as he was known, got really interested in the Crooks tube and set up his own series of experiments involving these cathode rays. And a fair simplification of what's going on here goes like this. What he would do is he would hook up two metal electrodes in the tube with a tiny hole in one of them. And so when you hooked up a power source up to this, what you would get is this beam of light that would move from the negative to the positive. It would be attracted to the positive, but it would be moving so fast that it would just pass through, and you'd get this beam that you could kind of measure, because when it would hit a painted surface over here, it would fluoresce or glow. On either side of the tube, he hooked up either charged plates or magnetic fields. He did the experiment both ways, but if we think in terms of a positively and negatively charged plate, he ran the beam through here. So without the plates, the beam would just shoot straight across in a straight line path, and it would light up on the right side. When he ran an electric current through these plates, the beam would bend towards the positive charged plate, which tells us, because of the fundamental feature of our universe, that like charges repel, opposite charges attract. It means that this beam has to be made of negatively charged particles. Particles, because the momentum of the beam changes. So it has to have mass in order to have a momentum change. So we have particles that are negatively charged. And you can actually measure what's called the charge to mass ratio by measuring this angle of deflection relative to how strong the charge is in the positive and negative plate. And so Thomson's able to make kind of three observations and conclusions, right? So we have the direction of deflection towards the positive plate tells us that we have negatively charged particles. Particles because their momentum is changing, which means they have to have mass. We can figure out the mass of the beam, not the bean. Should say beam there. That's a typo on my part. We can figure out the mass of the beam by how much it bends when a certain electric current is run through the positive plate. And what we find is that mass is more than 1,000 times smaller than the smallest atom that we're aware of at the time, hydrogen, which means we're dealing with particles on the subatomic level, something smaller than an atom. And then he went in and he changed the metals in the electrode to a bunch of different metals, and every single metal gave the same beam that deflected the same amount and towards the positive plate every time, which means every substance, or the atoms of every substance he used, must contain these negatively charged particles, which Thomson dubbed electrons. Well, what this tells us is that atoms are not sealed off to our view. They are not solid spheres that are indivisible, but there is in fact something inside the atom, or the atom is made up of parts, and at least one of those parts is an electron. And so what Thompson had to do was redesign the Dalton model to include these different parts. And so the first historical model of the atom you need to be aware of is the Thompson model. And the Thompson model is that the atom is a delocalized sphere of positive charge. So the positive charge is kind of spread out everywhere, and the electrons are stuck to it because negative charges attract positive charges. And it's the hooking of that electric current up to the atoms that forces these electrons to shoot off this positive ball as you overload your metal with negative charges. And when Thompson was asked to describe kind of how this model looked, he said, well, it's kind of like bread pudding. Of course, Thompson is British. This is a famous British dish. And plum pudding is like a bread pudding that has chunks of fruit in it. And so he said, the atom is like plum pudding. The atom itself is the bready part of the plum pudding, and the electrons are evenly dispersed throughout the medium like raisins in plum pudding. So I don't know whether or not you like bread pudding or raisins in your food, but according to Thompson, this is what our new model of the atom must look like.